Okay, this video is we're going to talk, in this video, I'm going to talk about the formation of the ozone hole in the Antarctic. Okay, so this is a polar ozone hole that occurs at the Antarctic, and it does because of special conditions that occur. And so here is the summary. Number one, it's winter and there's no light in the Antarctic. And so if there's no light in the Antarctic, you don't have your normal reactions that occur with light. Number two, you form polar stratospheric clouds. Polar stratospheric clouds. And this is unusual. You don't have these forming. They normally don't form, but they do in the winter in the Antarctic. And so three, we're going to have a different set of reactions that occur on these clouds. And we'll form a reservoir really of Cl2. And it gets worse than that, but the Cl2 is going to be a problem. The normal reservoirs are not happening. Because we have no light, we're not having the normal reservoirs, not occurring. And then we have springtime. In the springtime, we have light, and so we're going to have a massive change in reactions when the light hits. And that's it. So we'll go through some details on here. So normally we have the winter is from March to September, and springtime starts in September, the end of September, and it goes down to April, March sometime, beginning of March in here. We don't really care about how long it lasts. It's just this area around September that's important. Here are the normal reservoirs. We have Cl plus CH4 to give us HCl plus CH3, and the CH3, if you remember, exits the stratosphere, gets converted to CO2. Not a problem. We know that the HCl can go on to react with OH, but it's not a favored reaction. It favors this side. So we have this reservoir of HCl forming in normal conditions. The other reservoir is ClO, and it reacts with NO2 to form ClONO2, which acts as a reservoir containing the chlorine. Remember, chlorine is the implicated species. And what we're going to see is in the springtime, we're going to see light hitting and we're going to see a massive release of chlorine, all because of these polar stratospheric clouds. So I've told you already that normally we don't have any stratospheric clouds. There's no water up there. Normally no water, so no polar stratospheric clouds on this. There's just not enough water. But in the winter, there's no light, so you're not destroying the water. It's not reacting, and it gets very cold, minus 80 degrees. There's no sun, and so we don't have the typical reactions that heat up the stratosphere. There are two of them. O2 plus O yields O3 plus heat. It's not happening. The reason it's not happening is there's no light converting O2 to 2O, oxygen atoms, and therefore we have this reaction not happening, 2O going to O2 plus heat. And so you get cooling of the stratosphere, massive cooling. It will drop down to somewhere around negative 80 degrees C. Then there's another thing that happens, PV equal nRT. And if the volume and the moles and R are all constant, then you know that if the temperature decreases, then the pressure has to decrease. This, along with the Earth's rotation, causes a polar vortex. And so this vortex, it isolates the air in the stratosphere. Therefore, we're going to concentrate all reactions and species in the vortex, which is occurring above the Antarctic. So the other thing is, vortex is going to last well into October, which means we're going to have isolated air, and we're going to have light hitting this vortex because it's become springtime. Springtime starts at the end of September. So we're going to have this very cold polar stratospheric clouds, isolated air, and we're going to have light hitting it. So let's talk about our stratospheric clouds. The clouds consist of H2O, HNO3, and sulfuric acid. This HNO3 is going to be pretty important. So on the surface of the clouds, we have new reactions. We have ClO, NO2. Remember, that's our reservoir. And we react it with water, and we get HOCl plus HNO3. And this is fine because it's night, nothing happens on there. But when light hits, we're going to react the HOCl. So as long as we have these polar stratospheric clouds, we remove the reservoir. Our ClO, NO2 gets converted to HOCl. We also have on the surface HCl. This reservoir gets converted to H plus aqueous plus Cl minus aqueous on the surface of the clouds, the surface of the water droplets. And then finally, we have Cl minus plus HOCl forming Cl2 plus OH minus. And so we're starting to build up, chlorine gas in the stratosphere during the dark winter because of these series of reactions. If I follow it, I'm converting the ClO NO2 into HOCl. I'm converting the HCl to Cl minus, and then those two react to form Cl2 gas. That's the sequence that happens on there. So this chlorine is growing, Cl2 is growing and accumulating in the stratosphere. So the other thing that happens is this chlorine is isolated. It can't move in or out of because of the vortex. Vortex isolates the chlorine in the Antarctic, in this hole it's going to form. So now we build up a cloud of Cl2 gas, and then the Cl in the springtime, we have light. So now the reaction that occurs is Cl2 plus H nu, light, gives us 2 Cls. So Cl is a catalyst in mechanism 1 and 2 for destruction of ozone. Also, the HClO that's on ice, it also reacts to give us OH plus Cl. And so we have a massive release of chlorine due to the light. Mechanism 1 and 2 occur for the destruction of the chlorine. And so this vortex lasts well into mid-October. The ice crystals last for months. And so some other things occur. We have Cl plus CH4 going to HCl plus CH3. Okay, and the HCl now is still, because we have ice, the HCl goes to H plus Cl minus in the ice. And then Cl minus plus HOCl gives us more chlorine gas. All this occurring in the stratosphere. We also have this reaction not occurring. So we have light and we have this reaction that normally occurs, but it's not occurring now. And the reason it's not occurring is all our 8NO2 has been converted to HNO3 in the clouds. And as long as it's in the clouds, it's not in this reaction here. Okay, and it gets even worse because some of the HNO3 is removed from the stratosphere. And this is because these cold polar clouds can sink into the troposphere. And so you have removal of NO3. And so, you have multiple factors removing NO2 in here. And so as long as I have these polar stratospheric clouds, we have destruction of ozone. So when the polar stratospheric clouds disappear, then we go back to the normal set of reactions. And we remove chlorine by getting it in these two HCl and ClO2, NO2 reservoirs. Now, there are other things that happens. Now, the polar vortex is gone. As it warms up, as the stratosphere warms, polar vortex disappears. It goes. And so the ozone pore air, stratospheric air, can move out. And it does. And New Zealand and Australia can have some low O3 levels. And that has been recorded. Okay, that's the end of this. I'll talk more about these reactions in the next video.